So let's start. Wow. So this talk is titled Mechanism Design for Data Science. And the main purpose here is to, in addition to say happy birthday to Joe, is to explain to you what these pictures are all about. And hopefully we'll do it in this short amount of time. But while preparing this talk, I also told Yoram about that. It brought me some memories that I have from Joe that he for sure he doesn't remember, but I remember very well. In ITCHA 89, it was my first conference talk, and Yoram, my academic father, introduced me the first time to Joe, my academic grandfather. I had a crazy talk on a topic that I now looked, it was crazy. So there was a paper that I say here, let's move AI from logic to interacting Markov decision processes, let's incorporate robust solution, let us put all of this in a game theoretic setting, and let's integrate all of this in a regular structurable manner. Sounds nice comparing to what we had there. And this was like a spring of AI, so there were many people in the audience. There were a huge audience, but no question. And then after the talk, I asked Joe, was it that bad? And I still remember Joe's reaction. It was very good. No reason someone in the audience could grasp all of these new topics. And then it continues with the paper itself that got, for a young PhD student, very extreme reactions. Some love, but some hostile. I will not talk about it in length. And I had some brave fights at that time, and even some thoughts about academics. And then I remember, really remember, Joe's reaction to the paper. He sent me a message that I can find even to this. He said, nice paper. I would change the example after lemma 3 to something. This was amazing. No love, no hate. He actually read the paper. And it really, at that point, really restored my beliefs somewhat in academia. So thank Joe for that. And in the talk today, it will remind you that a little bit. So now we still talk about AI, and whether we have an evolution in AI or evolution in AI, and you'll understand towards the end of the talk, I hope that I'll manage that, my opinion. But you know, all of the buzz that has been created recently with really extreme statement, like Google CEO says AI revolution will be greater than the invention of fire, electricity, or the internet. And you know, all of these kind of, especially because of ChatGPT or whatever that became things popular. But I was lucky to be exposed to this very, very very close manner in the recent years. And I must say that amazing things are going on. And just to give you an example that is already from 2 years ago, things that I've been involved with. So for example, you can just write, you know, everything that appears here, not in boldface, really just write it text, but asking it for some short spec of a Python program with an example of the program, and then ask for another program, and then ask for what will be the program, and it will output you the program. In fact, it's quite amazing. And you can say, oh, this is simple program, there is much progress, but you know, people that really live and breathe all of this idea that combine generative AI with what is called pre-training, which is basically based on huge amount of data, that static data that you understand all of the web in particular kind of way, and the architecture of the transformer. All of this is not a topic of my talk. Really, you know, finding just examples when these kinds of things don't work, you know, sounds a bit naive to people that know where this goes. And so in this talk, I'll just say, so what is missing?
I have a question.
Yes.
Why does between 2 and 13 include 2 but not 13?
Sorry?
Why does between 2 and 13 include 2 but not 13?
Didn't catch. Oh, I don't know. It's okay. Very nice attention. So anyway, I'll tell you what I think is missing. Again, there were quite examples that we heard yesterday from others. So many of the things are evolving very, very rapidly. So what is missing? And I think there are 3 topics that are missing, and mine will be the third one. So much work on, or attempts for, or believes in the need to incorporate discrete and symbolic reasoning, a classical form of failure of neural approaches. In fact, also people are not great in this, but this is really a failure. On the other hand, also much work emphasizes overcoming issues for explainability, causality, ethics, which are known failures of powerful machine learning approaches that exist even prior to the revolution. What we emphasize for quite a few years, but it became very, very active recently, is what we call the multi-agent economic system perspective. We'll go and give you the three categories that I think are relevant. These will be the pictures, but basically it means that the data that we talk about here have issues. We don't, as long as we talk about minimization over huge amounts of data, I personally believe we are in a good shape. But the moment you come to a situation where you understand that data may be used by competitors, or that should be shared by co-competitors, or the fact that data is dynamic as far as strategic behavior, which is the main use, by the way, of now of these languages, then you are a problem. In fact, to the mathematicians among us, it's not be about mathematicians, when we move from the minimization problem to a non-cooperative setup, then things become tricky. And in fact, every time that we go and try to understand, put it in an ecosystem, then we get this kind of problem. So I'll try to give you these three examples. And if I have the time, even one of them will be a bit more technical. This has a theoretical part and highly experimental part. This will be about all the theory side. So first picture. First picture is that we bring data from the same pool of data. So this is what I called strategic machine learning. So in clustering, for example, we group a set of objects in a way that the objects of the same group are similar to each other, are in the same cluster. But in fact, when you go to and talk about the competition setup, the ecosystem, it's not the case. In fact, what happens is, in fact, we need to choose centroid solutions, locations, such that the interaction to your location is maximized. Again, to the game theorists here, it really sounds like facility location games, but it's actually what it is. If you do segmentation of your users, you don't go and you do the same segmentation as your competitor. It will be ridiculous. So this is what's actually going on. So we need to look at this kind of thing because of we drink from the same pool of data. Or regression, that will give a more technical example. We need to, in the classical regression, we'd like to estimate the conditional expectation of dependent variable given the independent variable. And here suddenly we'd like to maximize the probability of being the most accurate, the more accurate about our opponent, and so on and so forth. So in a very quick example, this is, in this, we try to use all of the, just thing will stay in the family. So I'll use work for Omer Ben Porat, now a faculty member in the Technion, which is a grandson of, of Joe, my former student, great students. That appears in NURIPS 2017. It's based on ideas that already appears in Stock 2011 in the work that's called dueling algorithms. So the idea as follows here is that you have some state-of-the-art algorithm. Here we just use it linear regression, but the results go not for more complicated algorithms. And you have some data, and you'd like to predict based on the data something. Here it's just predicting the apartment value based on the apartment size. Now you'd like basically to compete with this state-of-the-art algorithm, which is Bob, that come to the play. So what happens now? Here it's just depicted for the training set, but basically you like that after you train your algorithm, when a new point comes, you'll be better predictor than the other. So that's what is the tricky point, and this is actually what we need. So it's not, you need to minimize mean square error, you'd like to be just better predictor than the other. And this requires extending, PAC learning or whatever, the machine learning framework, but just to show you how it works, just some glimpse of the algorithmic part. It's very simple picture here. So think you have some just simple linear regression just for this example. So you have 3 points and you have this current algorithm. So in order to best respond to this algorithm, what does this mean? For any point here, there is a range that you can win against this point. And in the parameter space, it translates to 2 parallel hyperplanes that you win. So each point translates to 2 parallel hyperplanes, and together you get, if you look at all of the points, you get what is called an hyperplane arrangement. And in this hyperplane arrangement, in fact, you'd like to find a region where basically you win the largest amount of points. And this can be done efficiently. It should work and also generalize nicely. So this will be the idea. You just change the problem from minimizing square error to do something like best response regression. So I not tell you the theory, but I say, look, you can take real data. We talk to statisticians and say, oh, try it on the Boston housing that we started with. So actually, you can take the algorithm. You basically, every number which is written here that it's greater than 0.5 means you will be able to defeat what is the algorithm that is used, which means in most of the cases, you'll get better prediction than the algorithm that is used. And there is no contradiction here. So we can say, oh, this happens because, you know, basically in some cases you do really badly, right? Otherwise, it's impossible. So it turns out that you can massage this algorithm and also do something that the mean square error, the ratio to the mean square error will not be that bad. As long as you have basically more or less the same computational power than this kind of algorithm. So in general, what I wanted to sell to you this picture is you really change the problem. The problem is not now the classical minimization one, but it's different one. Actually, what we do in our work, we move from the fact that we have here best response to a game theoretic recommendation. It all started for a very realistic problem where a cloud service provider need to provide prediction services to competing parties. So what can it do? They compete. So there is a notion that we defined, it's called regression equilibria, that basically offer to you prediction algorithms that are themselves are in equilibrium. Just to give you the feeling that what we're, yes?
You never said in those slides what Alice was doing and what Bob was doing. Was one of them doing linear regression and another using a different strategy?
Yeah, so the best, first of all, we didn't formalize it, so we didn't say it, but I'll answer very, so in order to build best response regression, the techniques here are, it can be any deep learning algorithm that you can refer to. Yes, you can do, you can be very weak for the first result.
Was one of Bob and Alice using a best response and the other was using standard linear regression?
This was what was written here. There is a notion that we call, I define the best response regression. What was depicted here is, yes, what happens if both of them try to respond to one another? Then you get a game, and there is a notion, it's called regression equilibrium. So there are many subtle points here, but they are all in fact handled in this theory that includes several papers. One of them talks about regression equilibria, which is for a game theorist is what they want. But to be honest, you can really defeat state-of-the-art algorithms very nicely here by best responding to them. Second picture, which is the second item, which I think is the big one that is missing. So I envy all of the biologists, so I'll tell you about that. And you know, so the idea is as follows: there is a lot of discussion about data sharing, and data sharing is crucial, the contribution of data. So, but the metaphor that I use, which is really what is actually going on in a realistic setting, is the following kind of thing. See, there is a story that I was told about the zebra and the ostrich that have a very nice kind of synergy. So the zebra has a very good vision, but is very the sense of smell is really bad, and the other way around for the ostrich. So they have a very nice synergetic kind of way that they help each other, escaping from the tiger. But the tiger will eat only one of them. So we have here a condition. Lions, fine. So I'll tell you now about the big lions. So we have now a situation of collaboration between competitors. The place where it comes to reality, now to talk about real big tigers, there is something like called Azure Retail. What Azure Retail tries to do? Basically, to make connection, for example, between retailers in order to compete with an Amazon, or with Amazon, but in general, with an Amazon. So what we have now is these guys can like to collaborate, but they are also competing. In fact, this refers also to this hot topic that is called federated learning. Federated learning basically talk about trying to combine the learning capabilities of different kind of parties and the data of them in order to share them in order to have better predictors. Again, here we have parties that have on their own incentives, and they really don't like to share it because the algorithm is well designed for that. That's reality. That's really blocks. I'm even not talking about healthcare kind of situation where the situation is much worse. So we need to move from what is called federated learning to data sharing design. So from the pure point of view of the firms, it's not clear that sharing data is necessarily beneficial. And even if it is, it's not clear that sharing all data is optimal. So how do firms share data to maximize joint profits? Also, data sharing scheme may harm the consumer welfare. The question is therefore extended to design of such schemes that benefit consumers. So can we do something that will be Pareto improving to the environment? In fact, I'll give you one example. This is again very general, that to the economists in the audience we saw the minimalistic example where it shows. This is the hoteling setting from 1929. So those of you that have seen it, it's a classical setting. Consumer tastes are normalized to be selected uniformly in the interval 0, 1. Two firms, one in 0, one in 1. The firms decide on what is we call base price to consumers that say don't know anything about, and personalized price for consumers that know the taste. And the consumer value from a selected product is 1 minus, which is 1 is just a length here, its distance to the selected firm, and the utility is the value from the product minus the product. That's very classical. What is the new thing here is that some consumers are known to both firms, some only to one of them, and some to none. Should I share the information? So we started from that, and the baseline is no data sharing. Let's not share the data, just use the distribution. Full sharing is good for consumers because we get price competition, of course, but not for the firms. It will be harmful to the firms. But it turns out that there are data sharing schemes which are Pareto improving, considering both firms and consumers, and what I call individual rational and incentive compatible. That's all of this kind of work is not with our relative, it's with Ronen Gradwal, my good friend. And basically it was a surprise to us. You can really do data sharing that will help everyone. In fact, the result here is in a much general setting. The previous very stylized hoteling example can be extended to whole data sharing design paradigm, where the canonical application, I already mentioned it, is competitive data sharing, can be used for general recommendation systems, where there are two types of data sharing schemes in the form that we call mediators. The mediator basically tries to integrate the data from the different schemes, either where these are competing parties, or they are competing parties that even need to compete in a sense with an external entity, like the Amazon competition with the retailers. And there are also optimal mechanisms that we provided for the general setting. So I know that I'm going fast, but I just want you understand the picture here. So in the first one, the idea was that we drink the data from the same pool, and basically we are competing. And in the second one, we are in a situation that we are competing parties, but we have incentive to share. And these are really the situation where actually people say, I don't know what to do here. And basically because it doesn't fit the minimization framework. And the last one that I like to spend the most time on, until I'll be blocked, that really bothers us for quite a few years, and I learned a lot about this, is what is called the dynamics of data. This is real pain. If you like to join me here and understand what is the real pain that I think that should bother us, this is this one. And not the crazy stories about what is going on. It's just, it exists, by the way, for quite a few years, but the deep learning revolution, let's say, just put it into really make it, even more severe. And at the end, it refers to some herding phenomena that we get in the content that is created, basically, and the base of this herding phenomena, the corpus that we get and we use is really, really biased towards particular kind of issues. So let me give you an example. And the example is, I use this one because now I think by now it's already recognized. For my partners in Google, for example, already have group dealing with this kind of thing, which is the recommendation system ecosystem. So typically users and content are represented in the same latent space in the machine learning literature. So in deep learning is very simple. There is content, there is user, everything is embedding in some space, and you just look for the closest, nearest neighbor. Each user is matched with the closest content in his taste. Very simple. And this maximizes the welfare given the available content. The problem is, which is really, that in the ecosystem, there are publishers, they care about their payoff. So basically, you look at your payoff and you change your content. By the way, the most popular strategy that really lead to the herding phenomena is that you look at the winners and you try to mimic them. But let's put it aside, that's very experimental, and this talk is quite clear. So but there is some loop. So basically, things are changing. The data is not static. You change what you publish, and now you can generate more content. So the question here is, what do you do now? Do our system that just do nearest neighbor with these huge embeddings is really good? So this is something we've studied for many years. Here, especially, there is much work on search with my colleague Oren Kurland, and much more, and some overview papers already in CIR and other places. But again, I'd like to show you in examples that will show you how we, as in the academic theory, had already can really help you. So I'll use the following motivation. It's very simple kind of setting. Think about there are only 3 content types, X1, X2, and X3, and 3 users. Everything here can be scaled. U1, U2, and U3. And the numbers that appear here are just user satisfaction from the corresponding content, or the click-through rate, if you wish. So player 1, which is content provider, can provide 2 types of contents. Player 2, just 1 type of content. So what current system do? All of these nice computations, embedding, whatever, at end, what happens is it shows to the most satisfying content to each player. So this player 1 get 2, payoff of 2, let's say every user works the same, just for this example, and player 2 just 1, and the total satisfaction of the user, let's call the social welfare for this example, is 0.9 plus 0.9 plus 0.2, which is 2. But if player 1 will just provide this, then the satisfaction will be higher, 2.6. But of course, player 1 will not do that because it will now get only 1 user. So that's in the spirit of price of anarchy or whatever, but it's real pain because it hasn't been noticed, all of this type of situation. So what should we do? So how we decide which content to show? So we started by some axiomatic approach, which means here are things that when you talk with practitioners, they'll never give up. One of them we call fairness. It's not fairness, it's a big word to say fairness. It's minimal requirements. It says like, if a user has 0 satisfaction with an item, it will be displayed with probability 0. No one will argue about what is called here fairness. And the other one that everyone that was dealing with ad auctions and stuff like that already knows that people care about stability. They like that the system will converge sometime. So you can say that under any set of players, users, and items, the induced game should possess a pure Nash equilibrium. In fact, they like to add that any better response dynamic will converge in game theory terms. So we'd like to have this fairness and stability. And the moment that, and now let's find such mediator, such recommendation system. So it turns out that if you like the system will be complete, an item is displayed with probability 1, I'll do it in 3 minutes, then no mediator can satisfy fairness, stability, and completeness. So we should try a different approach. And bear with me for this approach because it connects suddenly many theoretical things. If you lose me, that's the time to reconnect. Focus on an arbitrary user, UI, and a strategy profile with strategy of content, X. And now look at the subset C of the content providers. It's just a tuple of contents. So you can define the user UI satisfaction for the items of the players as the maximal satisfaction you get from this context. So everything is very natural, but those of you who know some game theory, we just defined what is called a cooperative game. We have all of the coalitions and a number associated with each of one of them. And now we can have what is called power indices for these games. One of them is the Shapley value. And the Shapley value has nice properties in other kind of contexts, and also the properties that it sum up to 1. So basically, we can define the probability distribution. So we define the recommendation system or the Shapley mediator that set the display probability according to the Shapley value, the Shapley mediator. So we find a way that start from non-cooperative games, go to cooperative games, define tutorial distribution, and use it as a recommendation system. And suddenly we have nice properties. The game induced is a potential game, so any better response dynamic converge. And so its shifting mediator will satisfy fairness and stability. And in fact, if you like to be a real theorist, it can be shown to be, if you add what is called economic efficiency, then the only mechanism that satisfies fairness, stability, and efficiency is the Shapley mediator. By the way, this is not a result of the Shapley axiomatization. And what bothered me is that any time that I've seen Shapley used, the problem was that the computation was intractable, was very nice. So it turns out that computing the display probabilities here can be done in linear time. So in a sense, I don't say use it, but actually it really I need to wrap up. So I just say wrapping up. All of this has another angle, which is very practical one. And this is the one that really bothers me the most, because we can actually show that we can attack with building bots, these kind of systems in a way that will write some content, will make us the winners, will make also others try to mimic us in this kind of dynamics, and in this case deteriorates the content, the corpus content. That is very real. So we'll not talk about this. There were several PhDs here. So let me sum up. If you ask me whether we're in evolution or revolution, my answer will be we are in revolution time. Don't be misled by showing some examples. We are in revolution time. The problem is, in my view, is that we are in revolution time in what is called autonomous agent. We build wonderful autonomous agents. But when you put it in an ecosystem, and it's recommendations, search, even autonomous cars, we get some problems. So, for example, competitors should not exploit the same algorithms as they have the same data. Competitors would need to share data in order to succeed. And corpus data change dramatically to the competition. These are the three things that we isolated. And these are the pictures. And this is the whole agenda that I'll be more than happy to talk about. There are many acknowledgements, but I need to finish. I just say one thing. These five guys, I didn't know anything, not about IR, not about NLP, not about experimental economics, not about building deep learning system, and about language modeling several years ago. so they deserve a lot of credit, and happy